Just started recording again. Okay. Hello, everyone. Welcome to our presentation titled "All You Need Is Consistent Promotions." Today, Tim and I will be walking you through some interesting promotional planning problems, some issues that we faced while using machine learning for it, and then some interesting solutions that we've come up with. A little bit about ourselves. Tim is a data scientist on my team. He has a master's in statistics from the University of Toronto. He's a very avid biker, and his research interests include demand forecasting and partially observed time series. Me, on the other hand, I'm Kanchana. I'm the director of data science here at Kinaxis. I got my PhD in computer science from NC State. I teach at the University of Toronto as well as Ryerson University. I'm a mommy to a 2-year-old, which is a big part of my job. And finally, I'm very, very passionate about building productized and scalable machine learning solutions. So the agenda for today will be, I'll talk a little bit about what we do at Kinaxis, specifically what our machine learning looks like. I'll introduce the problem of promotional planning in retail. I'll talk about a few issues that we faced when building machine learning for this problem. And Tim will then wrap it up by talking about the solution that we came up with for the issues we faced. So a little bit about Kinaxis. So Kinaxis has been an integrated business planning and a supply chain company for over 30 years. They have one integrated platform that's used by over 10,000 users in more than 75 countries, and we're a leader according to the Gartner Quartet. We also have customers across many different industries, such as automotive, consumer products, retail, and so on. And many of the top names in these industries happen to be our clients. So machine learning in Kinaxis specifically is surrounded around some key teams and key platforms. So the big one being the data platform that helps us ingest customer data, as well as some external dynamic signals such as flu, weather, holidays, and so on. We have a very complicated machine learning as a service platform that helps us orchestrate and scale and schedule and manage all of our machine learning tasks. And at the core of it all is our machine learning solution that has all of our common culprits: the feature engineering, the forecasting piece, the training, the evaluation frameworks, as well as an optimization engine that is used in certain of our use cases, like, say, a flyer planning. Apart from that, we are also quite involved in R&D activities, and we have a lot of collaborations with the industry. We have two teams across Ottawa and Toronto who both publish, I would say, on a reasonably regular basis in collaboration with the industry. We're also quite popular in a lot of these speaking circuits, from International Symposium of Forecasting to the Toronto Machine Learning Summits to other conferences such as the Strata Data Conference and some workshops at ICDM and so on. All right, so that's a little bit about us. So now to the core problem that we're dealing with. So promotional planning in retail is actually a very, very important and common problem that happens for almost all retailers. So as a category manager, as a person who's in charge of a certain specific types of SKUs, say shampoo or bath soap or something like that, they always have to answer the question of what is the best promotion I can put this product on, given some constraints. So let's say that I want to run this promotion in, say, 6 weeks' time. I want to maximize margin. I want to keep sales constant. And somehow I have additional constraints, like how much will the vendor fund my promotion and so on. So they have to keep making these decisions almost on a periodic basis, say every few weeks or to every few months. And often they have a bunch of levers that they can play with, say a promotion type, maybe the percentage of discount that they can apply on the product, maybe where on the flyer they want to put the product, maybe additional things like potentially running it in Ontario alone and maybe not running it in BC, potentially opening it up for certain loyalty people, like, maybe folks with certain number of points, say, people who earn more than 1,000 points, or maybe even opening it up for certain target groups like, students or seniors and so on. So there's lots of different settings that they can try. And their goal is to figure out the setting that actually gives them the best business benefit. This problem is actually really interesting and important. In fact, in the 2021 retail trend, this was actually stated as the third most important trend that's going to happen in retail. Kinaxis, of course, has a tool for it, which is called the promotional planning tool, which does exactly what I said. You have all of these levers, you play around with these levers, and then you can compare different scenarios and then see which scenario actually gives the best business benefit. The way that it's solved at the core of it all is obviously a machine learning model that's going to give you some prediction of the number of units a particular product will sell, given some constraints. You compare different scenarios. You find the scenario that gives you the most, say units sold for the constraints, and then decide that that is possibly the best promotion to apply on that product, on a given date and time. Of course, this sounds really easy. It's a machine learning model. Throw in some features, perturb those features, see what the output looks like, and then make some decisions on that, right? I mean, it sounds pretty simple. Of course, it's not that simple. And let me tell you why. So the law of demand, as you may, law of demand basically says that if all things are equal, right? If you keep all of the levers the same and only change the price of the product, then hopefully as the price decreases, the quantity sold of a product will increase. So if you put something on a 20% discount versus a 40% discount, then the 40% discount one is basically going to sell more than putting the product on a 20% discount. That's the ideal. Of course, the reality looks completely different. So the expectation is the one on the left with the nice linear trend, but on the right you have these very complicated curves where somehow putting a product on 20% discount sells a lot less than when you put it on a 0% discount. And that intuitively just doesn't make sense, right? Like, why would something at full price somehow sell a lot more than something at a 20% discount, assuming all of the other parameters are kept constant, right? So this was a challenge we faced because we had to give the end users a planning tool where they could try many, many different scenarios. But then the outputs of those scenarios has to somehow tie in with your logic, right, of how you expect these promotions to behave. And of course, the actual demand curves did not follow some of those trends. And that's what we were trying to solve. Tim will now walk us through what kind of solution we came up with.
Yeah, thanks, Kanchana. So, why are the curves not conforming to reality? Like there's really not a lot of reasons. So first is that that all things equal, this assumption is really hard to achieve. Like unless you have experiments with A/B testing, you're not gonna have that. Retailers, traditional brick and mortar retailers aren't really set up for that. The second point is really that true demand is always changing. You can try to control all factors, but the fact is that no single day is exactly the same as any previous day. There's also confounding factors that you may not observe in your data. Reasons include clear-out sales. The second reason is that not all all possible promotions, the coverage is not adequate. Promotions are costly to run, so most times past promotions are used as templates for future promotions. So here's our proposal. So instead of dealing with the ML output on the left side, we want to have the best fit that is aligned with economic assumptions, and that's the right side, the green line. You can see that it's mostly non-decreasing as you go to the right. And so how did we figure out this problem? So in ML, problems find you. That's different from most industries. So what the user sees is that when they tune offer award, so that's how much discount they're getting. When they increase that, the forecast units actually drop. So from this perspective, all things are equal. And when they increase discount, the forecasted units decrease. And that's not desirable. So what do we want? There's only actually two things. First is that increasing discounts should not cause a decrease in predicted units sold, and that's the monotonicity requirement. And the second requirement is a bit more on the UI side, like it's that we want smoothness. When you change discount, you have a small change in discount, that should give you a small change in the predicted units sold. So we achieve this with two steps. The first step is to apply isotonic regression, and the second step is to take the output of the previous step and pass it through a monotonic interpolator. What are these two steps? So the first step is isotonic regression. Basically, it gives you a piecewise linear monotonic fit. So this is a piecewise linear curve that minimizes the squared error. The second step is monotonic interpolator. So if you choose any interpolators, it will give you a curve, but it's not guaranteed to be monotonic. Linear interpolators always give you monotonic if your input sample is monotonic, but that's not true for higher order interpolators. So an example of something that preserves monotonicity is this p-chip interpolate that you can import from SciPy. So you can see that there's the dots represent your input sample data, and the curves dip somewhere between 4 and 5. That's not what we want. We want a monotonic interpolator. So the adjustment procedure looks like this when you put in the two steps. First, you actually have to identify the driver setting in your promotion. So a driver setting is something that corresponds to a higher discount and therefore corresponds to high predicted units sold. So for example, if your promotion is a buy X get 1 at P% off, if you increase that P, you are expecting more units sold. So P, that is the driver setting. So the second step is to apply isotonic regression on the forecasted values. So you do need to generate data sampling the values of P. You need to run whatever feature generation that you need to run, and you need to pass that into the ML model. So you end up with P, sampled values of P, and the predicted values of P. And these are what you send into the isotonic regression. You get a function out of that. And for the third step, you want to figure out values of P for which the model output jumps. Because if you're just applying to all the values of P, you're just going to end up with a non-smooth curve. So once you figure out where the jumps are, you put that into the monotonic interpolator, and it will give you a nice curve that satisfies both monotonicity and smoothness. So here there are two metrics that we use for the quality of adjustments. So recall that the two steps earlier define a change in the curve. So the first metric is the relative, it's the amount that is adjusted. So that what we measure is the L1 distance of the adjusted curve minus the original curve. So the distance between the two curves, you divide that by the L1 norm of the original curve. The smaller this value is, the less your adjustment. So that's good. That means your original curve satisfies the requirements pretty well. The second metric is the non-responsive zone. So that's the longest interval of driver settings which do not cause a change in the predicted units. So if the user is tweaking the driver settings and not seeing any change in predicted units, that's bad. So here's a good adjustment. You can see that the blue curve obeys the law of demand pretty well. So we can see that in a small relative L1 difference, that's only 3%. And the non-responsive zone is pretty small. That's because most discounts happen between 0 and 50%. This is a bad adjustment, so this is also what we showed earlier. We can see that the amount adjusted is significantly higher at 7%. And also the non-responsive zone has increased by a lot. You can see that because from 0 to 30%, the predicted unit zone is decreasing, and that ends up being flattened out. And this is the worst adjustment. So you can see it in the metrics as well, that the amount adjusted is really high, and the non-responsive zone is pretty close to the entire range. So this will trigger a flag. Chances are there are issues with there might be confounding factors. Maybe this product is being phased out. So there might be factors that our model is not picking out that leads us to have this incorrect demand curve. And here's the last bit about computational cost. So so the more settings there are, the worse it's going to get, and it's going to get exponentially worse. You can see that, for example, if you have 2 settings, you're going to end up with, so if it's a biax-scaled 1 and p% off, so x has only 10 possible values, it's an integer, but p is a float, so you need to sample that. If you sample 100 points, you're still going to end up with 1,000 rows, and as you recall, during the algorithm, you have to send the 1,000 rows to feature generation and model prediction. So it does scale up significantly with the number of promotion settings. So here, there's a bunch of options that you might want to try. So what we've talked about was a model agnostic adjustment. When you can't really run experiments. So if you can, then you can tease out the all things equal. The effect of that. You can also have model-based monotonic restrictions if you know that you're restricted to a single model type. And that's it for our presentation.
Thank you, everybody. We're also hiring, so do check out our website, and we're happy to answer any questions. Thank you very much.